All right, there we go. Oh, wow. My voice, cool. All right, so thank you everyone for hosting me. I didn't time this, so if it goes a little long, tell me to shut up and I'll speed it up. My name is Dr. Mike Rushanan, and today I'm going to present a little talk about medical device security, what could possibly go wrong. So, building medical devices with security by design. And I hope that's good for a systems oriented talk because we'll talk about some of the gory details of embedded systems and TLS and things like that. So, a quick who am I? I'm this good looking guy right there. That's the only time I've ever wore a suit. So my CEO is very happy with me. I'm the chief scientist at Harbor Labs, which is a medical device cybersecurity company. Um, and to just put it shortly, I help medical device manufacturers get to market. What does it mean to get to market? Well, essentially, these are regulated devices. You have to prove to the FDA you're not going to kill anyone, and then you can sell your device. Profit, yay! We're all happy about that, right? At this point, I have worked on over 100 devices with over 40 medical device manufacturers, ranging from startups to some of the big names that I can't say because it's being filmed, and I'm sure there's an NDA somewhere. Another note about me, I'm just a lecturer at Johns Hopkins, specifically the Whiting School of Engineering. I offer classes in security and privacy and computing, which is like a foundational course for the Information Security Institute. And I started teaching a medical device cybersecurity class, which is the first of its kind, where I got really good reviews, which means Hopkins is going to keep letting me do it. So I'm pretty stoked about that. Thank you. Oh, yeah. And then I'm actually a lot older than people sometimes think. I'll take it as a compliment, but the gray hair says otherwise. Sweet. So, what are we going to talk about today? Well, integrating embedded systems with cloud connectivity is actually transforming healthcare. You're like, wow, thanks, Mike. That's an elevator business pitch. There's a point behind it, right? So it's a common architecture. We'll talk about why they're common architectures that make these things. If you're doing IoT or SCADA, you're like, yeah, we do the same stuff. But the difference about medical devices specifically is that these architectures actually improve patient health outcomes, right? There's an important part to it being that like a person's livelihood can be based on the use of these devices. Now, with that innovation comes significant risk. So an insecure medical device can have fatal consequences, right? So this is a personal journey for me. I'm a diabetic, so I've got a CGM right now. Don't look at my sweaty arms, but it's a Libre Freestyle. It checks my blood glucose levels all day. If that device were to say malfunction or not give me the proper range of where my blood glucose levels are at, that could be dangerous, right? Because I might take too much or not enough insulin. Too much is worse. Not enough just makes me sleepy, angry, Mike. Too much, maybe coma, Mike, and nobody wants to see coma, Mike. That would be bad. So in this talk, now that I've kind of set the preface for it, we're going to dive into what medical device manufacturers can and should do, also sometimes fail to do, and apply secure by design principles. And so to make it a little bit more fun, once I get into that part, I'll give you real world examples of some of the crazy stuff my manufacturers have said to me. Love you, manufacturers. You know sometimes it's crazy. And just kind of how we talk them off a ledge or help them come up with a better design. Alrighty. Now, agenda. Pretty straightforward. It's going to be two parts. Background on terminology. What is a medical device? Just so we're all clear. Regulatory history. What is that? What are the requirements? And what is security by design? How does it apply? I'm sure we're all systems folks. We get what a design is. We get architecture, but how do you start to incorporate security from the beginning? I'll make no assumptions. I know sometimes it's not really something we focus on. We focus on build the thing as fast as possible, give me MVP, and push it out the door. Then I'm going to do a device design walkthrough. So I want to build a medical device in real time with y'all. I'm going to step through some of the problems, what could go wrong, give you some of the anecdotes, and maybe even talk about some of the mitigations, so a better design to help us build a better device. Cool. So background and terminology. Quote Dijkstra, why not? Humble brag, let's go. Let's do a survey. So how many people know what a medical device is, or like use one personally, or know someone who used one? Yeah, I figured most of us. Yeah, I'll go with a strong 90%. How many people know that medical devices are regulated? Wow, that is when I started as a regulation, what's that? I just build whatever I want. All right, how many have heard of medical device classification levels? Class 1, Class 2, Class 3? Let's go, we have some people, that's fantastic. I'll still cover it, so don't worry. We're gonna know the jargon, we're gonna know the vernacular, it'll be good. How many people know the FDA requires medical devices to be secure? Yeah, at least one person. 2 people. Let's go. Okay. We'll see when that happened, and then I'll leave you to your own conclusions if you think it happened a little too late, a little too soon. Love the FDA; they're doing perfect things. You make your own, judgments. I won't say anything. So, what is a medical device? Well, a medical device can be an embedded system, desktop, mobile application, cloud backend. Why not? We have some AWS people here. A lot of my manufacturers are using AWS. Some mistakenly use Azure. Some use GCP. I don't know why. Examples of medical devices include continuous glucose meters, insulin pumps, which are pretty cool. You can actually use your phone to control those things. ECG halters, surgical robots, and infusion management pumps. So this runs the expanse of medical devices, all kinds of stuff. It's really cool, right? Now, in terms of the medical device architecture, like I said previously, like it shouldn't be shocking. A medical device is a system of systems, right? Okay. So what does that mean? Well, it's pretty simple. A system of system, you can have an embedded system. That thing can communicate over like Bluetooth or Zigbee or something. Wi-Fi is totally cool. You could have an iPad or an iOS app to control it, because why not? That iPad is going to have cellular connectivity. What does that buy us? Well, that buys us connectivity to the internet no matter where we go, regardless of sort of Wi-Fi availability. And then you have cloud backend, because folks want to do ML AI, because that's where the money's at. And so cloud backends make sense. You can do all of that there. You have paid for infinite resources. Maybe that's a nice way to say it. Just to be clear, though, a medical device doesn't need to be an embedded system component. It can be just purely software. And so the FDA has given this a name: software as a medical device. Will I ever say that again during this talk? No. I just want you to know that it exists as a concept. And to give you an idea, you could have a medical device that takes your glucose data, do trend analysis, give you some insights. That would all be software, because they didn't make the CGMs. They just made the back end to process the data. That is still a regulated medical device. A lot of folks don't know that. When you first get into the market, you might not try to go to the FDA. You might just try to sell your stuff. Cool. So I also need to, and I'll be very brief, cover regulatory history. So the FDA in 1938, its regulatory purview extended to medical products. Cool. So 1938, that's a while ago. I wasn't alive, neither were any of you, I hope and assume, but that's when it started. Then in 1976, the FDA said, look, we need to have a risk-based classification for medical devices. We'll get into what that actually means, but basically, is it so risky it could kill you if it didn't work right? Or is it, won't hurt you at all, whatever, nothing changes? Now, the FDA recognizes the use of international consensus standards sometime in 1997. So this is definitely getting in when I first started, working. And it's an important concept or note, because like now we have ISOs and AME and some of the big standards bodies giving us the blueprint to do like these designs correctly, properly, and reproducibility. It's all good. So then the FDA releases its first cybersecurity guidance, 2014. Pause. I'll let you get the feels. I said I wasn't going to say anything. In 2014, I remember this particular standard, and it was really focused on just using the NIST cybersecurity framework, which is a totally good framework to use. It was just kind of that. And so to give you an idea of, well, why'd you just trail off ellipses, just kind of that? Well, in 2014, the guidance was 17 pages long. In 2023, the final guidance is now 57 pages long. So the FDA, I mean, this is a credit to them. They really started focusing on cybersecurity. They realized what the problems are. They recognized those problems. And it was important from a regulatory perspective to actually have tighter controls on what are you doing? Why are you doing it? How do you prove that you're doing things well? And also, if the secure by design concept starts to get floated, how for the total product lifecycle are you keeping this thing secure? So some other regulatory requirements that I mentioned, but I'll go quickly because I don't know how interested you are in this, but just so our vernacular is aligned, risk-based classification. The FDA classifies devices based on patient safety, or the risk to patient safety. And essentially, we have class 1, class 2, class 3. So class 1 is like a bandage or a hospital bed. It's a classification of medical device. Also a crutch, right? Your crutch hopefully doesn't have cybersecurity components and embedded systems, because wow, we are all screwed if that happens. Class 2, moderate risk, CGMs, infusion pumps. So like this is a diagnostics device. It tells me what my blood glucose level is, but it doesn't control my insulin therapy, right? I do that. I'm a human in the loop. And so that's why it's not of a more higher risk category. Class 3, pacemaker, doesn't work, not a good day for the person with the pacemaker, right? Typically, these always include implantable medical devices for obvious reasons. There's a lot of risk to implant it. There's a lot of risk to maintain it. 7+ years, maybe without firmware updates in the early 2000s, just sitting inside of your body doing a thing. There are regulatory pathways. I'm going to breeze through this, but essentially, the FDA has set these pathways. This what's called a 510(k), a de novo, a PMA, for you to go to get your medical device approved for sale. So it's a pre-market activity. Now, I've been using these terms, and I apologize. I didn't explicitly define them. Bad mic. Pre-market is before you go to market. Pretty simple, right? So you'd be designing your product. You'd be setting user needs and requirements, verification and validation. You'd be doing all those processes in the pre-market because you're building your device. In the post-market, the FDA is also interested. Device gets sold. That's not it. You can't just hands clean, whatever. You now have to enact processes to be able to manage and monitor vulnerabilities over time. And there's some key takeaways that I forgot the circles for, but this really big one should stand out. The age-old adage of software engineers, software ages like milk. And it's true. Because if you were to do sort of a probabilistic modeling of software over time, the likelihood of there being a vulnerability actually increases. Though this is some qualitative magic that I'm just kind of waving my hands at. You'd be like, well, Mike, probability quantitative. Like, no, I'm just making stuff up. But it usually holds true that as software ages, there may be a vulnerability, maybe because of what it links, maybe what it's based on, maybe the foundation, etc. Cool. All right. So secure by design. What does that mean? Well, it means incorporating cybersecurity for the total product lifecycle. Buzzword, TPLC. You'll see it. You'll hear me say it. I'm lazy, but that's what it means. Core principles. How do you actually do secure by design for the total product lifecycle? Well, you do threat modeling. You do cybersecurity risk assessment. You look at your third-party software components because we're software folks, right? A lot of us here. How often do you check if a version of a library you're using, either you installed it with pip or cargo, you actually check to see like, oh, is this vulnerable or not? So that's a really important concept for medical devices because like if you have a vulnerability anywhere in your software stack as a part of your product, as packaged, that means that your entire system could be potentially vulnerable. And then lastly, fancy words to say, do you have any bugs? And do they have cybersecurity implications because of it? And those are sort of the core principles. I should also not axe out, but cybersecurity testing. So we'll see exactly what type of testing you would conduct because there are various different types depending on like what we're talking about. Is it verification versus validation? But ultimately, all of this matters because we're talking about patient safety. That's what sets us aside. Like that's why we're different than IoT devices. Why we're different than SCADA. Why we're different than desktop PCs. We don't want to kill people. So, how does secure by design actually apply? Well, we look at the user needs. The device needs to be secure. I mean, the user cares about that. What are the requirements? Those are going to actually meet the user needs. Formally, we're going to look at design and development, verification and validation, production, distribution, maintenance, and decommissioning. All of those things matter. That's all total product lifecycle. So just to give you a quick example, a user need here is that the user needs assurance that their insulin delivery system is accurate and it can't be altered by unauthorized actions. Seems pretty reasonable. We would have design requirements. And these could be system requirements, it could be software requirements. It really depends on how y'all go about your business when you're developing your products. But the insulin pump shall connect to authorized iOS devices via BLE 5.0 or higher. Seems reasonable enough. The pump shall enforce LE secure connections. If you don't know the difference between LE secure connections and legacy pairing, you should definitely check it out because lots of folks use the Nordic NRF SDK. They use the default code they found on the internet. They come to me and I go, whoa, yeah, that crypto's not good. And it's easily man-in-the-middle, something to keep in mind. Pump shall use BLE out-of-band pairing mechanism. This is authentication. This is important to the connection. Pump shall cryptographically authenticate all iOS device commands. So in this little contrived example that I have, iPad's controlling a pump, no biggie. From a design and development perspective, we apply a threat model. I didn't tell you the threat model. I don't want to delve into all the different ones. Microsoft Stride, if you want to Google later, just happens to be one of them. And we like to think of these design requirements in light of our threats. So if we're thinking about like a spoofing-based threat, we would think about an attacker trying to just arbitrarily take their iPad and connect to the pump, right? That would be bad. And when we think about it that way, we go, no, 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 I've done security by design. I've already sort of thought about these types of threats, and I've already built in security requirements. Well, at least that's the way we're supposed to design our device that would mitigate the risk of spoofing. So it's hard to authenticate arbitrarily to an insulin pump if, for example, you're doing BLE with LE secure connections and you have an out-of-band pairing mechanism. That would make life a little bit more difficult for the attacker. So continuing along the example, verification is great, right? So we do software verification every day. We do systems verification. So what you're trying to do here is prove that your device design is, it's secure, right? So you're trying to prove that your design has been implemented and that, our primary focus, obviously, security. So in terms of a verification protocol, you just attempt to pair the pump with an arbitrary device, or maybe you do a source code review. This is not breaking news to y'all. This is probably what you do in your software jobs, right? It's just applied from the cybersecurity perspective. Validation, we want to prove that the device actually has security, right? So you might have a third-party testing shop come in. They could do vulnerability testing, CVE lookups. They could do penetration testing. So connect to the device, run Nmap, run some BLE tools. Light Blue is a really good one. If you've never heard of Light Blue, Google it. It's a nice tool. Connect to anything, doesn't really matter. It's just arbitrary. It doesn't look for the typical broadcast advertisements. If it speaks Bluetooth, it'll connect to it. Cool. So I'll pause. Feeling good? All right. Got a lot of background, got a lot of terminology, little tech stuff injected, because why not? It's a tech group. We're going to talk about the device design walkthrough. So let's go ahead and build something together. Now, I'm going to give you an architecture. I want you to copy it in your mind as quick as you can, because I'm going to click off the screen. I'm just kidding. I'm not going to do that. Very common architecture that a lot of folks would probably appreciate or could recognize. It kind of steals from the contrived example earlier. But we're going to build a cool new embedded system medical device called CardioMic. I didn't want copyright laws to get me, so CardioMic it is. A patient wears CardioMic. CardioMic is going to capture an ECG signal, electrical signals of the heart, not a big deal. It's going to collect those signals. It's going to connect to an iPhone and an iOS application. Why? Well, so that we can send data to the cloud. There are two specific users in this example. It's going to be the physician and also the patient themselves. So the patient's wearing the embedded system. The embedded system's doing its job, sending some data off to the cloud. The physician can then log in to probably a web app, right? That's hosted on the cloud, and they can access that data in real time and look at some trends, whatever else it might need to be. So what could go wrong? Anybody want to take a guess? What could go wrong? Maybe one guess. That's cool if no one wants to. All right, it's easy though. That's definitely one of the things could go wrong. Or you get denial of service, which is bad. Yeah. So literally every single circle represents a place where security could go wrong, and it's a lot. It's everything actually. So the key takeaway here is, well, you're speaking HTTPS. Cool. Over what? Well, TLS. Great. What version of TLS? 1.2. What about perfect forward secrecy? How can you guarantee that? Well, I've got to speak very specific cipher suites. Something to keep in mind. We talked about BLE, iPad, iOS security. Are you running the latest version? Is it a jailbroken device? Did you let anyone, arbitrary person, bring their own device? All those things actually matter. Cool. So I think the best way to kind of break these things down now is we're going to decompose that architecture. Just walk through every individual component. Not every single one. That's a lie. We have a limited amount of time, so we'll talk about some of the cool ones. So we have an embedded system here. If you guys squint, you could probably tell it's one of the darlings of the community, Raspberry Pi. Why not? I have seen Raspberry Pis in medical device design before. Let's talk about that later, not on video, and see how y'all feel about it. So Raspberry Pi incorporates a Broadcom SoC, ARM-based Cortex thing, no big deal. Interfaces with an ADC because it's going to pull in some ECG data. It runs an operating system, and we know that operating system to be not on this list, but it's Raspbian, right? So it's a Debian-based distribution. It's Linux. It's not a real-time operating system. That also has implications for your device design, but hey, here we are. There's also exposed physical interfaces. There's USB, there's GPIO, there's serial wire debug. There are all these things that actually exist on this board that we can tap into, right? So what could possibly go wrong? Well, Bluetooth and Wi-Fi weaknesses. So we just talked about one earlier, Bluetooth 5.0, do LE secure connections. Why? There's something called elliptic curve Diffie-Hellman ephemeral, which is a secure key exchange. Totally want that. If you're using the legacy connection, that was the Bluetooth standards body, the SIG group, actually invented their own crypto and come to find out it wasn't strong. This was the right way. Pairing modes without a screen. Like, oh my God, my Raspberry Pi doesn't have a screen. How do I pair with a pin? You don't. So that's something that you would have to think about. That's something that could go wrong because if you just will allow just works pairing, which is trademarked, but I forgot the trademark, you're gonna have to think of a better way to be able to authenticate devices. So this is typically done, say, on the at the application layer. People just bolt it on. WPA support, don't laugh, but think about the patients, right? They're not all just young, healthy folk, or they could be young, sick folk, or they could be older, sick folk. You don't know, right? You don't sort of know their technical level of competence. You don't know where they're gonna connect to. I mean, they might go to Starbucks and connect to the Wi-Fi, why not? And that's always scary. Don't do Starbucks Wi-Fi, trust me. Unauthenticated UART and SWD. Happens all the time, work with a lot of manufacturers. They need these interfaces because they need to debug the devices, especially if it's like, oh, look, it's broke. Let me ship it back, an RMA, it's gotta get fixed. And so they'll argue, hey, Mike, I gotta leave this on. There are really good, smart methodologies and methods to be able to secure that. You can actually do like public key-based authentication over those interfaces. That's the right way to do it, but it could go wrong if you do nothing. Serial console with root access happens all the time. I try to log in on a UART, baud rate 9600, boom, gives me emulated a serial terminal, and then I type root, hit enter, doesn't query me, doesn't ask me for passwords. I'm like, yeah, I'm root, cool, hacker. Sometimes I type root, hit enter, and it goes password. I go, root. Enter, hacker again. Yeah, so those are things that could go wrong. We should always think about those. It's a Raspberry Pi. It has a default password too. So if you just Google what the Pi default password is, that's another thing that I like to do. If I know who manufactured the board, I might just look up what the default password might be. Read-write access to memory, always bad. It should have write access to memory still enabled over your JTAG interface, for example. Obviously, you can just dump all of ROM, not a good thing. You can look arbitrarily at any sort of the RAM register, or excuse me, CPU registers and other things. Not good. Another thing that's kind of unique, I think, to some folks that never really thought about this, not blocking USB devices. So USB supports a lot of different interface types, right? So it can be just mass storage. It can be an Ethernet adapter. It can be a Bluetooth adapter. These are medical devices. Like, no one's ever going to plug a Wi-Fi dongle into a medical device. Like, yeah, they do. I don't know why. They think it's a good idea. Like, it's something that needs to be considered. Oh, and a really, really cool one that I think, depending on like your comfortability with hardware versus firmware versus software, is that these SoCs have inherent hardware flaws, right? So we are all about speculative execution and branch prediction. We're like, yeah, processor processes fast. But ooh, wait, Spectre, Meltdown, like, oh, you can access arbitrary parts of memory. Oh, that was supposed to be a feature. Oh no, what am I doing? ARM processors, Intel processors, this is inherently baked in. How do you fix it? Well, you load microcode during the bootloader that basically says bad processor, don't do that. Or you have to wait for the kernel to do its thing with a kernel module, which slows everything down. And this is an embedded system for a medical device. You can't have it be slow. Your infusion management pump is like, oh, I'm gonna pump some insulin like whenever I want. Not a good look either. Anecdotes from the real world that I get literally all the time. Mike, physical access isn't realistic. Like, that's a lie. The first thing I do when I get your device, I tear it down, because why not? Usually it'll go, but Mike, we use special screws. All right, well, that is a T10, and it's a torque bit, and it's a jeweler's set, which I keep in my bag wherever I go, and they're small ones, so the TSA doesn't take them away from me anymore. We cannot disable debug ports. Again, we got an RMA at Mike. Like, what are we going to do? And usually my answer is like, well, depopulate it. Like, don't make the job for the script kiddie easy. Take the thing off. Also, it's a PCB. Break it off, and then you throw it away if it doesn't work. But that tends to be one of their major concerns. Another thing that's happened to me maybe more and more frequently, is a mischaracterization, but it's happened. I take the device apart, I see an SD card, I see compact flash, I see a USB dongle inside of the chassis. And I think, huh, I wonder if that's encrypted. So I take it out, put it into my laptop, and huh, not encrypted. All right, game over. Hacker man, they pay me a ton of money to do these things that I think a lot of people could probably do without me, right? But it happens. There's design constraints, there's design limitations, there's a lot of factors, there's business things that I don't understand. I'm not a business person, but all those things come into play. All of those things should be considered as a secure by design, right? We have to think, well, those are my interfaces. How do I protect against them? Well, if you're doing Raspberry Pi, something called Lux encryption, right? So you can do full disk encryption using Lux, which is really neat. Cool. Time check. I started at 7:10. Awesome. Oh, God, yeah. I'll go a little bit quicker then. Firmware. So this is a Raspberry Pi. It's a two-stage bootloader. First stage is in ROM. Second stage is literally on the SD card if that's what you're using. It can run a Raspberry Pi OS, which is Debian-based. And so we know like sudo apt install package, and that's how we're going to build our medical device. It's a multi-user environment, right? It supports multiple users, groups, has file-level permissions based on that. Linux 6. Something kernel, I guess. I stopped paying attention to Linux kernel versions after 4 because I'm old, but yeah, cool, 6. And that's going to have all the drivers, right, for our interfaces. Userland, for running CardioMic and applications, we need a userland to be able to run the CardioMic application. Network stack, another really important one. No one wants to implement the TCP IP stack. Why? Because when we do, we typically get it wrong, and that becomes a whole suite of vulnerabilities as well. So what could go wrong? Well, lack secure boot. You're like, oh, wait, Mike, secure boot? You can do that outside of Windows? Like, yeah, totally. It has different names and different monikers depending. Maybe it's called verified boot. Maybe it's called trusted boot, depending on the device that you're looking at. But really, all you're trying to do is authenticate the firmware. Say like, yes, this is authentic firmware. Mike made this because he signed it, and the integrity is still there. It hasn't been changed after the fact. So that SD card example, without secure boot, I pop it out, I go in, mount the root file system as read-write because I got power, and I change a bunch of stuff, and I pop it back into the medical device, and no one's none the wiser because guess what? The firmware wasn't verified on boot. I just made changes. That's fine. Software is run with root privileges. Happens all the time. We go into look at a computer, and I think I can combine this maybe with another one on here. I don't have it. Don't run your applications as root. Doesn't make any sense. You're like, oh, but I've got to have access to like the serial communications interface, like this deb serial, because it's Linux. I'm like, yeah, it's a block device. I get it. Everything's recognized as a file. But also, there's a group called dial out. So just write a service level user. Don't run it as root. You're just asking for privilege escalation to happen if there's a vulnerability in your software application. Other things, Linux kernel, software application, library vulnerabilities, like you'd be surprised, libc can have vulnerabilities, go figure. Python interpreter versions can have vulnerabilities. These are bad things. Remote services get configured or misconfigured all the time. SSH, it's like, yeah, SSH, password-based SSH for root. No, don't do that. No root remote logins. Do public key authentication. There's a stronger way to do it. Just disable passwords entirely. Connects to malicious network, like that's a design limitation here because based on the design that we have, I said that CardioMic needs to work wherever you go. So it's going to connect to my iPad, but it also has Wi-Fi connectivity. And because of that, it may potentially just connect to Starbucks, and Starbucks is bad. Starbucks networks, sorry, Starbucks. Antivirus is disabled. It's Linux. You might say, well, malware, runclaim maybe. It's fine. You'll be okay. And bootloader vulnerabilities, basically trying to get a rootkit, trying to get ahead of your actual operating system, to kind of ingrain yourself in a way that you can't get out. Cool. I will do the anecdotes from real world, and then I think I'll skip to the last part. I don't want to be mindful of everyone's time. But anecdotes from the real world, again, physical access isn't realistic. Like, oh, if you're hacking a device, it is realistic. And in fact, just so it's clear to everyone, if you ever go like look at a DEF CON talk about medical device cybersecurity, it's because they went to eBay, found the thing, an old thing typically, buy it, tear it apart, connect to the interfaces, and go, look what I found. So I definitely want to strongly discourage just saying physical access isn't realistic. I think it's realistic. There's a lot of really strong security mechanisms that you can put in by design to protect yourself if someone has physical access, or at least really make their job difficult. File system mounted as read-only versus secure boot. Not comparable. Secure boot is the only way to do that. If you mount your file system as read-only, that just means if I can look at the Flash controller. If I can access Flash directly outside of the system, I can change things. A really fun one that I had when I was on a customer site is this BMC and IPMI, which is essentially remote access into your BIOS. I was like, oh, cool. Yeah, I found BMC is enabled. I try to connect to it over a web browser on like a local area network. The IPMI interface is so old, it served up SSL v3 and it served up TLS 1.0. The certificate was probably 10 years expired. And the username and password was, you guessed it, the default that I found on the internet, didn't have to do any work. And then I had remote access to a very expensive machine's BIOS. So just things that do happen in the real world, you gotta be cognizant about. Other things, I see really old versions of Android, Windows CE. Let's be happy and thankful the FDA is on the train. No more old Windows versions. So I'm seeing less and less of XP, and it's fantastic because why are we still running Windows XP? Cool. Yeah, like I said, I'll go. I just wanted to jump sort of to the end. I had a joke for Aaron though. It's like most of these apps are written in C and C++. Sorry, no Rust yet. Even if it was, they would disable any sort of memory protections anyway. So go figure. Cool. And I will skip through these. Why did I bring up C, C++? Memory corruption vulnerabilities, your classic buffer overflows. Still applicable. Go figure. Cool. Another really good anecdote. A lot of folks manufacture, not a lot of manufacturers, but it's happened to me a couple of times where it's like, hey, I'm running my app in kiosk mode. I'm secure. I'm using a Flipper Zero to make my presentations go forward. It has bad USB on it, so you can script a USB interface. And any 20-year-old who plays Fortnite knows that Alt F4 can get you out of the your full screen gaming application. And so we're on a customer site, and it was like, yeah, it's kiosk mode. I was like, Alt F4. Like, oh my God, you have desktop. You're an administrator. Like, yeah, hacker. I got it. Cool. Alrighty. Let me see if there's any other really good anecdotes. Oh, crypto stuff gets wrong all the time. Go to Wikipedia for the love of all that's holy. Do not use AES, ECB, electronic code book. It says in the wiki not to use it, so it's probably a good indication that it's not great. Think about authenticated encryption, AEAD, do things like AES GCM. Trust me, it'll make your lives easy. Do not use deterministic random number generators. There's cryptographically secure ones for a reason. They come with the libraries. It'll make your life a lot better too. All right. I appreciate y'all for listening to me. I'm sorry I'm 3 minutes over. It's been fantastic. I love that everyone's here and intently listening. I can take questions now. And again, appreciate your time.
Thank you. It's enlightening. You mentioned that there are requirements around a company being able to keep the software reliably secure for a long period of time after it's released. What are the mechanisms put in place? The companies go out of business all the time, and they get bought by people who listen. But how do they ensure that?
Yeah, that's a really great question. So medical device manufacturers are just like any other tech company, but with quality engineers and regulatory engineers mixed into the fray. And what's happening, or what I see now, is that typically when building your device, there's an FD&C, which is like a federal regulation for you to create a software bill of materials. So it's just a recipe list of everything that went into your system to make your application in your firmware. That list is typically fed into other tooling. A really good one is OWASP, O-W-A-S-P, like the darling of my community. They have a free tool. Also, if you want to pay Black Duck a ton of money, they have a paid tool that essentially takes that SBOM, carves it up, and it gives you a monitoring service that it's just doing a glorified NVD lookup. So go to the National Vulnerability Database and say, hey, Mike's got OpenSSL 1.0.0f. And it's going to be like, any new vulnerabilities? Yes? No? Maybe. And then if it finds a vulnerability, it just feeds it back, right? So it becomes sort of this loop. GitHub advisories is another really good example. Like if we're all using GitHub here, they started looking at software version strings, especially if you're using like a requirements.txt file, if you're a Python person. And it's actually pulling that version information in and giving it to you for free, which is really nice. So that all to say that there are processes, like there's tools and processes in place that actually enables this to happen. There's just regulation behind it that says that it has to happen. And once a manufacturer sort of gets the handoff, someone buys them or they just kind of spin out. I- or if they go dark, I hope no one's using their devices anymore. That's scary. If they spin out, essentially, because it's a regulatory requirement, the hope is that the purchasing or acquiring company continues to do the process, but they might just do it their own way then. Yeah. Does that make sense? Cool. All right.
Sorry, I go off over here. I can like project. Hey, thank you. I was curious the comment that you made about Rust, and like they would probably just turn off memory protection anyway. Is that because this is like they as the manufacturer here, right? Like the person in here making the medical device. Is this like, is there a compliance reason for that, or like there are regulations that haven't caught up about like that type of memory safety, or is that just like they might not be familiar with the technology? Like, where is that coming from?
Yeah. So first and foremost, I was being cheeky, but out of all the devices that I've analyzed so far, no one was using Rust. Now there is no regulatory requirement or oversight in terms of how you implement your programs, and it just so happens that a lot of times, like some of these folks are using 16-bit, 32-bit MCUs. You're not always like, hey, I have a Cortex A9, I've got a ton of processing horsepower, right? And I can do hardware-based floating points and things like that. So you may be limited in terms of, and it's not going to be like, oh, Rust is not efficient. I'm not going to say that, but what I will say is that the SDKs for some of these chipsets are limited, right? So like if I'm doing a Nordic thing, I'm probably using the Nordic SDK. It makes it a little bit harder for those teams to branch out or even try to customize their CMakes and bring in Rust, bring other language components. So I really think it's just a limitation on the embedded engineering space because a lot of the embedded engineers I've worked with is really comfortable and familiar with C and C++. And now they're running Python scripts. I'm not sure how I feel about that, but Rust will probably catch up. I definitely think it would. I want it to. Like I said, it's a darling in my eyes. I want memory safety and protection to be enabled by default. I just haven't seen it yet. Cool.
Have you seen any work being done with formal verification of medical devices?
That's a fantastic question. I wish that I could say yes, but I have not yet. So I definitely think that would be a really nice, I'd say research area first, just like what would the formal methods be and how would they work? Given the context of some of the code that they have, the legacy aspect, and I wonder even what's the big scary to some of the engineers that have already like have this medical device, like, oh, let me just do this formally, and what is that going to mean for my product? And it may even come down to, and I hate to be this guy, but sometimes it's just like a business decision. Like companies might say, well, what does it mean in terms of me to be able to sell my device? So I think it's a really astute observation. Definitely something I'd love to see. I just haven't seen it. I haven't seen sort of the focus on it. Yeah. Hey. Oh.
Well, I was also going to say, like, if no one is inside CRH pushing that at FDA, like,
Yeah.
manufacturers don't care.
Oh, 100%. I mean, manufacturers, if this is still filming, I love you. It's cool. Please keep hiring me. But yeah, I mean, it's kind of like, you have the FDA is the parent, the manufacturer is the child. The child's going to try to get away with whatever they can. And again, I don't mean that to be dismissive, but it's kind of like if there's no regulatory guidelines or boundaries to kind of force you into it, then yeah, they'd look at it as sort of just additional cost. And they're like, well, what's the benefit to me? And so again, another really astute observation, I think that directly applies. And that's why they're not looking into those things yet. In fact, I think that's where a lot of my business comes from cybersecurity, because folks were so just build the device and the clinical function, clinical function, clinical function. And then I swoop in as a consultant and I'm like, oh, security matters and the FDA is looking at it. But at that point, they might already be to the point, like they could come to me and like, I need you to do cybersecurity work and we're submitting in 2 weeks. And then, my hair gets more gray than it already is and my ears blow up and it's sort of a hard conversation. It's not hard in that like they don't want to listen. It's hard in that like you have to deliver bad news and then try to build them up and kind of get them in the right place. So even cybersecurity, even with all of this new guidance, it takes a minute for the manufacturers just to be on board. And go, oh, yeah, I know exactly what you're trying to do. Okay, and I'm supposed to do it? And like, yeah, your submission will get blocked. And as soon as you say your submission will get blocked, they're like, oh, shit, we should go do it. They're like, yeah, you should.
Is there a regulatory requirement that they like hire a firm like yours for a security assessment before they go to market?
Yeah, actually, in the guidance, it's not, so it's called guidance because it's not like prescription, but there's a lot of points in the guidance that I know your submission will be blocked if you don't do. But one of the points in there for penetration testing is that the guidance will say use a third-party penetration test shop because they are decoupled from your software engineers internally, right? So if we're just software engineers at your company doing security stuff, of course they're gonna be like, how do I write this test so it passes? And it's just like, you don't do that with a third party because I'm not there to do that. I'm there just to be like, oh, how could I hack this device? So yeah, precisely that. I mean, the guidance points to third parties. I think that's where a lot of my business actually comes from. Cool. All right, fantastic. That looks like it. I really appreciate y'all's questions. They were great.